keep going because nothing else to do. I'm gonna keep going. So yeah, I did 36. I made a video on this, and turns out there's actually a very simple relation that you can just use, that is v squared is equal to 2ax. Now this is very I mean, it looks wrong at the first glance. I mean, like, how can you use v squared minus u squared equal to 2as on a case where there's no constant acceleration? But if you check the derivation correctly, you'll see that in fact you can use this. So even though there's no constant acceleration, you can write a vector, so our acceleration vector, as some constant vector plus some vector that is always perpendicular to the x vector, that is in this case tau vector, right? So this thing is always perpendicular to the trajectory at all times. P vector, it is variable as well, right? I mean, that's obvious because the trajectory itself varies. So the simplest thing that we can tell these people is v squared is equal to 2ax. Yes, this is about speeds and not velocity. Yeah, that's right. But hey, come on. That's all I could come up with. Okay, let's go to 37th now. I mean, hopefully this is correct. Do they want an even more descriptive description, what am I saying, of this motion? I don't think so. Yeah, 37th. A point moves along a circle with constant velocity. Oh, okay, it's not constant. It's v is equal to at, huh? Where a is this thing. Fine. Find the total. So the velocity is changing. Why is this in numbers and not vectors? Okay, find the total acceleration of the point of moment. Sorry, what am I saying? Find the acceleration of the point at the moment when it covered nth fraction of the circle after the beginning of the motion. Really? Probably this velocity, that's just the magnitude of velocity that they're giving us. So then its speed is basically 80. So we want the time when it covers nth fraction of the circle after beginning of the motion. So now at this point, yeah, so you have basically given us the speed. So you will just have dx upon dt is equal to a times t, where x is the path length. So yeah, x is equal to half at square plus whatever initial it was. Initially it is 0 in fact, right? So when it covers nth fraction of the circle after the beginning of the motion, right? Then what will x be? It will just be 1 pi n of the circumference, which is just 2 pi r. That is equal to 1 by 2 at square. And it's moving along what? So we don't know about what it's moving. Wait a second. We just want the acceleration of the motion, right? Sorry, acceleration of the point. So yeah, if we just want the acceleration of the point, I mean, okay, you know what tangential acceleration is? Tangential acceleration is just a, and the centripetal acceleration will be v squared upon r. So no problem. The tangential acceleration is a, and what is centripetal acceleration? It will be v squared upon r. What is v squared right now? That will be a squared t squared upon r. So a squared t squared upon r. We can definitely do it. Multiply by a on both sides. So then it will be 2 pi r a and all that stuff. So divided by r. Yeah, you'll just have 4 pi a upon n. That is what a squared t squared upon r is. So there we go, 4 pi a upon n. We got this and that. So you have the acceleration. Yeah, but how do we want? We want total acceleration of the point at the moment when it covers n. Okay, fine. So n is 0.1 in this case. Whatever. So should I represent this as you know, vector, or maybe just give it the magnitude as the answer? I'm going to write it like that, as vectors. So our acceleration vector, that will be, so I'm going to use r hat and theta hat for the radial vector, and I mean the outward radial vector and the tangential vector, right? So this will just be a theta hat minus 4 pi a upon n r hat. Cool. And now in this case, n is 0.1, right? So now in this case, it will just be a theta hat minus 40 pi a r hat. Wow, weird. Fine. Okay, 38. A point moves with deceleration along circle of radius r so that at any moment of time its tangential and normal acceleration are equal in moduli. Circle of radius r so that at any point its tangential and normal acceleration are equal in moduli. Okay, nice. At the initial moment t equal to 0, the velocity of the point equals v naught. Find the distance of the point as a function of time and as a function of. All right, so yeah, we'll have to do this thing. First of all, just have dv upon dt, which is, and in this case, v is the speed. This will be equal to v squared upon r. R is fixed, I think, right? So you can just write dv times v power negative 2 is equal to 1 upon r dt. And then integrating this thing, so this will be negative 1 upon v. And this will be as v goes from, so whatever initial velocity it had and whatever final velocity it has is equal to t upon r. That should be nice. So this will just be 1 upon v naught minus 1 upon v is equal to t upon r. This looks weird. Fine. So at least now we know what the velocity, I mean the speed is. Sorry. So find, oh yeah, so the velocity at t equal to 0 is v naught. Nice. The velocity of the point is a function of time and is a function of the distance covered. Function of time, we got it. As a function of distance covered, so we need to find what the distance covered actually is. So s will just be, oh no, wait. This is bad. How do we do that? So dv upon dt, oh yeah, so actually it's not that bad. I mean, once you know what v square is, it becomes a piece of cake to just find the time dependence for Excel. Yeah, so like basically integration of v dt, that should be your distance covered, right? And then you have v as a function of s, so sorry, a function of time, and it's doable basically. Yes, I get that, but in fact, why not do something else? Why not write it like this? So dv upon dt, I will instead write this thing as v dv upon dx, where I should say ds, right? So yeah, of course you can write it like that, no big deal, because basically ds upon dt is v, and from there it follows. Cool. Now what can we say? We can say v power negative 1 dv is equal to ds upon r. So then integrating this thing, just have natural logic. Why is this? Okay, I don't like this, but you got it. So you got it. V upon v naught is equal to s upon r. So that's our other relation. So first of all, you have, so do we need to solve? Okay, whatever. So 1 upon v is equal to 1 upon v naught minus t upon r, and then you're gonna take the reciprocal of that, whatever. So v is equal to let's say it's gonna be r minus v naught t in the denominator, r minus v naught t. The top is just v naught r. Okay, that's one thing. That is velocity in terms of time, and in terms of displacement, sorry, distance. This will be v naught e power s upon r. This is crazy. Exponential, seriously. Okay, fine. So you got a covered. Let's go to b. B is total acceleration of the point as a function of velocity and distance covered. Fine. So once you have B, you can definitely figure out what acceleration should be. Oh yeah. So, okay, total acceleration. That's kind of not good. Not good. Total acceleration. You want like as a vector, right? Good thing is that the centripetal acceleration and tangential acceleration are the same. So you just need to find one of them and we'll be done. So v squared upon r, that will give us the thing, right? So squaring this, you can just get v naught squared r squared, and then you will divide by r anyway. This v naught squared r upon r minus v naught t squared. Cool. And this will be v naught squared e power 2s upon r, and that thing upon r. Yeah, looks about right. So our acceleration, that will be equal to this quantity. So first of all, we'll have this thing v naught squared r upon r minus v naught t, that thing squared, and then you will have the vector. So first of all, yeah, not using those coordinate representations, I'll just say this times theta hat minus r hat. That should do it. And it's also equal to v naught square e power 2s upon r times the same thing, theta hat minus r hat. All right, cool. This is done. Let's go to, is there any CO for this thing, or okay. Wait a second. All right, B done. Let's go to 39. A point moves along the arc of a circle of radius r. Its velocity depends on the distance covered s as so basically like v squared is equal to a squared s, where a is a constant. Find the angle alpha between the vector of the total acceleration and the vector of the velocity as a function of s. Alpha between the vector of the total acceleration and vector of velocity as a function of s. Oh, okay. So when it says that its velocity depends like this, basically its speed depends on the distance covered. Huh. I think it's a constant acceleration case because, so yeah, I mean, you can say constant acceleration because it's going to be dv upon dt, not dv vector upon dt, but it still works out. So it's always tangential. So doing the same whole thing, I mean, what was that? v dv integration of that thing is equal to integration of a dot dx, right? So these are in vectors and everything. Now, if your acceleration, okay, you can just write it as tangential acceleration times x, like that, right? Cool. And then you would integrate this thing. So if your tangential acceleration was constant, then you can definitely write v squared is equal to 2a tangential acceleration times whatever path length was there. Oh, it should be dx, but hey, whatever. ds, sorry. That makes perfect sense, right? Yeah. So the same thing happens over here as well. Over here, what we have is v squared is equal to, so I don't want to differentiate this and do all that. No, I won't be doing that. I can, of course, but why do it? So a square of that, a squared s, right? So you can see the similarities. Over here you have a squared, over here you have 2a. So from it you can say that the acceleration was half of a squared, where w is the acceleration. I don't like using w, but whatever. Find the angle alpha between the, so yeah, you got what, oh, this is only the tangential acceleration, sorry. So tangential acceleration is half of a squared. We still don't know anything about the centripetal acceleration. Actually, that's not that hard to find out, because if it's moving on a circle, it's just v squared upon r. So v squared upon r, that's just a squared upon s, all that stuff, right? So the centripetal acceleration is just a squared s upon r. So this is variable and nice. Okay, so now what do I do with it? Find the angle alpha between the velocity, the vector of total acceleration and the vector of velocity. Oh, so you need to find what acceleration vector is and what velocity as a vector is. Hey, okay, this is just stupid because the velocity is gonna be along the tangent, so theta hat, and this thing we already know what tangential acceleration and centripetal acceleration, so it's not that big a problem, right? So no big deal. Tan alpha. Wait, I should just draw this. So this is your v vector like that, and then this is a vector. So this will be your, sorry, w vector, whatever. Makes a difference, maybe. So, oh, it's not like this. Centripetal acceleration is what this thing is. This is the tangential acceleration. Fine. and this would be our angle alpha. So alpha is just, so tan alpha is just W centripetal upon W tangential. That should make sense. So this upon that, right? A squared S upon R upon A squared upon 2. So this cancels. Just have 2S upon R as the thing. Perfect. Right, so you got it as a function of S. Nice. So you can just say alpha is tan inverse of 2S upon R. Though maybe tan inverse is not the best way to describe this, because nah, I'll just use tan inverse, whatever. I'll say the acute angle and not give it sine or whatever. Then it will work. 40. Particle moves along arc of radius r according to the law L equal to a sine omega t, where L is the displacement from the initial position measured along the arc. Wait, what? The displacement measured along the arc. It's not making sense. Huh? But you said it's displacement, so how can it be measured along the arc? But does it even make sense though? What does it mean to measure along the arc? You can't give displacement as an angle. It's just not correct. If this is the circle that's moving on, it's initially over here, then it's finally over here. This will be your displacement, and you want to measure it along the arc. How would we do it? Maybe you will take each of these and then find its projection along. No, why? Why should we do that? Because it could be mapped to here, or this could be mapped to there. What guarantee it is that what we find is what they are looking for? I think mostly what they are saying is that this length is L. Okay. Okay, AWR cost. Fine. In that case, it's doable, but right? You will need what angle this is, and because oh god, this is not making sense. Measured along that arc. You can see like whatever vector was over here. So if this is the vector that we're talking about, okay, and this is that vector, we just have to take the dot product or something, right? So how much is it along that? You could say something like that, right? Of course. But then that's just multiplying by cosine theta, and well, that would wait. Are you multiplying? Yeah, you are multiplying by cosine theta. Then this turns out to be weird, right? Oh, come on. What? How do we do this? How should we interpret this thing? I'm going to interpret it like this arc length is L. That's it. I don't know. It might not be. It might really be that they're taking projections on the arc and doing something with it. But that's just unnatural. Why would somebody want to do that? I'm just going to say the arc length is L. Fine. In that case, it's very much doable. The L is a displacement for me. Okay, fine. A and omega are constants. Assuming capital R, okay, so they give the radius. A and omega they already gave us. Fine. So what do you want? The magnitude of the total acceleration of the particle at the point L equal to 0 and L equal to plus minus A. Oh, so it's doable. No big deal. Okay, let's move to the next page because this is really, it's gonna consume a lot of space. So let's do it. First of all, we'll find what the speed is. So the speed is just, so it's dl upon dt. Where did it go? Okay, L is equal to A sine omega t, right? So it's gonna be omega A cosine of omega t. Now this speed, you can see like the velocity is completely tangential all of the time, right? So it's not radial because then the radius would change, of course. Yes, and now we'll go for tangential acceleration. So that will be the rate of this thing. which is going to be omega squared negative, right? So negative omega squared a sine omega t. Weird. Initially, is it so they don't know what is happening initially. Oof. Okay, actually we can do it. So initially t equal to 0, your v is in fact not 0, and that makes perfect sense, right? So you got this thing, and man, this is something like harmonic motion, whatever, and centripetal acceleration, that will just be equal to this thing squared upon r. So that will be omega squared a squared upon r, that times cosine squared of omega t. Right. Now what do we want to do with it? We want to find the magnitude of the total acceleration. So with this thing square, square root of all that. Oof. It's just okay. So at points L equal to 0. Okay, let's do it. At L equal to 0. Wait, what? Oh, okay, so L as a function of time, whenever that is 0, right? So if L is equal to 0, then sine omega t is equal to 0. Then this complete thing, it just becomes like tangential acceleration 0, and the centripetal acceleration, so yeah, centripetal acceleration, that will be omega squared a squared upon r. That's it. And at L is equal to plus minus a, what will that do? So plus minus a, okay. Oh yeah, so at that point your sine omega t will be plus minus 1. So then you will just have tangential acceleration is equal to minus plus of omega squared a, and centripetal acceleration will be 0. So hey, you just want the magnitude, right? Man, this thing is gone, it's just in one direction. So omega squared a squared upon r, let's go with it. Yes, total acceleration, right? So this will be omega squared a squared upon r and omega squared a. That's it. That's our magnitude of accelerations. Fine. Next. Oh, yeah, so this is a b part, right? Let's not erase it right now. B is the minimum value of the total acceleration and the corresponding displacement. Okay, cool. So total acceleration has the magnitude, right? You just want the magnitude of acceleration. So omega squared, I'm just gonna use a squared. Okay, so we already have a over here, that's why we have to use but man, omega is already used as well. So w, I just hate this notation, right? At points it seems like it's omega. I don't know, is this book old? Because nobody uses this anymore, everyone uses a. Anyway, is it supposed to be square of the square of that? Let's add them up. So omega power 4 a squared sine squared omega t plus omega power 4 a power 4 upon r squared, and then cosine power 4 omega t. So omega power 4, what I'm thinking is that we can switch this as 1 minus cosine squared. So this will be, and you can also take a squared out, so a squared, and now it will just be a squared upon r squared times cosine power 4, right? And then this thing is just 1 minus sine squared, so sorry, 1 minus cosine squared, and there we go. Nice. So talk about this function, it's just a squared upon r squared cosine power 4 minus cosine squared plus 1. This is a quadratic in c squared. So in 0 to 1, when is this thing the minimum? That will happen when you have c squared is equal to minus b upon 2a, right? Minus 1 upon 2 times of this quantity, which is 2a squared, and then we've got r squared right there, which can happen. Yes, it can definitely happen. So no big deal. And what do we want? Right, so the corresponding L value and acceleration value. Fine, very much doable. So whenever this happens, you can just say, and yeah, so sine was this, and I just wanted the magnitude as well. So since we just want the, I mean, this really is just harmonic motion, right? It's like a pendulum basically. So along that arc, your Your arc length is oscillating between positive and negative. I get it, no big deal. From here you can say, okay, sine of omega t, that will just be equal to, so okay, first of all we should go for cosine of it or not. So this will just be plus minus square root of 1 minus r squared upon 2a squared. That goes for it. So your L value will be plus minus square root of, so you can take that a inside, and now it will just be a squared minus r squared upon 2, right? And at that point your W min, that will be, so it's either positive or negative. Wait a second. Oh, we want the minimum magnitude, or do we want the minimum? Okay, which of these is positive? Yeah, it doesn't make sense because the velocity is changing. So what direction do we say to be positive? I don't know. Then we just say the minimum magnitude. Fine. So yeah, that's actually easily found. So just put that in there, or just use negative d upon 4. So omega for a for 4a squared negative d, so it should be negative b squared minus 4ac. So yeah, negative b squared is like 1 minus 4 times of this quantity. It's 4a squared upon r squared, and that upon 4a, so 4a squared upon r squared. Amazing. Yeah, it's going to divide by that, so omega power 4a squared 1 minus r squared upon 4a squared. This is even crazier. And then multiply by a squared right there, so omega power 4 into a squared minus r squared upon 4. That should do it. Square root of that thing, so it's plus minus sorry, it's omega power 4. So it's plus minus, what did happen? What happened exactly? Omega squared and then square root of a squared minus r squared upon 4. Next question. Minimize this, looks ugly. Okay, 41. 41 is, where did it go? A point moves in the plane so that its tangential acceleration is this thing and its normal acceleration is this thing, where a, b are positive constants and t's time at the moment t equal to 0. The point was at rest. Find how the curvature radius r of the point trajectory. Oh wow, this is another weird question. So they gave us the tangential acceleration as a constant. Then from this you can figure out what, so doing the same thing as we did before, you can just say v squared is equal to u squared plus 2as. So in this case 2, yeah, exactly, a, they use the same symbol as I wanted, so 2as. This is awesome. Or I should say 2a dot s, right? So probably, okay, no, and actually acceleration is just changing every time, right? So a s, of course, but a is just some normal number, and its normal acceleration is this thing. Now how do I use that? You got what v square is. Oh, and initially point was at rest, so we can cancel this. And how the curvature radius of the point trajectory, and so the curvature radius is just v squared upon yeah, I mean, like it is always directed along the trajectory, right? The v vector is always directed along the trajectory, and that means your normal vector, right? I mean, okay, this is obviously doable. So v squared upon the normal acceleration, so that will be 2as upon wn, which is just b t power 4. So you got it in terms of time. Isn't this awesome? But still, s is not in terms of time, so it's not yet done. Okay, so you in fact want it completely based on distance s half, so you have to find time dependence anyway. So yeah, what do I say of this? So v is equal to square root of 2s, right? Or you can just use s is equal to vt plus half at square, because yeah, so like half at square, that should work, that should really work. But still, just go with the proper way. So we can just integrate this. I mean, like this thing is ds upon dt. So you will just have S power negative 1 upon 2 ds is equal to square root of 2a times t. So integrating this thing, it will be plus 1 upon 2 divided by that's like 2 square root s is equal to, so integration of this thing. And by the way, s is just some positive number and everything, and you don't have to worry about it. Really. Cool. So this will be square root of 2a times time. Oh, it should be dt, but hey, integrate that, just get t. So square this. 4, or first of all, divide this by that, so this will be 1 upon square root 2. Cool. Then square this. So s is equal to a upon 2 times t squared. Exactly as we want. So you got it. You got what the displacement should be. I mean, sorry, the distance level, not the displacement. Cool. Yeah, so you can now just plug t power 4 as, okay, so let's do it. T square is equal to 2s upon a. T power 4 will be 4s squared upon a squared. Plug that in here. So just have this radius of curvature as 2as upon b times 4s squared upon a squared, right? This cancels, just get 2 over here. This cancels, and then that goes on the top, so a cube. Yeah, this got cancelled, so just that. Then 2bs. Exactly, so we can just report that in there. A cube upon 2bs. All right. What else do you want? It's 42. Wait, no, it's 41. Sorry. So that's it. That was the whole question. Let's go to 42 now. Wait, what's this? Okay, that's from previous video. Okay, a particle moves along the plane trajectory y of x with velocity v, whose modulus is constant. All right. Find the acceleration of the particle at point x equal to 0 and the curvature radius of the trajectory at that point if the trajectory has the form first of a parabola y is equal to ax square and of an ellipse. Okay, this is how do we do this? So it moves with a constant velocity. Acceleration of the particle at point x. Okay, so you have to find acceleration anyway. You can just keep on differentiating this. That would be really not good to do. It's a constant velocity, you say, so yeah, the path that you cover, that will be just v times a. So basically what you can see is like vx squared plus vy squared is equal to v squared. That is our only thing of usage from this thing. And so now let's go for a. Let's see. So it's a parabola y is equal to ax squared. If I differentiate this, you just get vy is equal to 2ax vx. Putting that in there, you will get vx squared times 1 plus 4a squared x squared is equal to v squared, which basically means that vx square root of 1 plus 4a squared x squared is equal to v. So basically dx upon dt is equal to more or less I'm getting it. But what if it's mod of, yeah, that is a problematic thing. Y squared is equal to 4, sorry, wait, what? Y is equal to ax squared. It can be going like, I mean, yes, your dx upon dt can probably be negative. That is also something that can happen. Okay, then what do we do with it? Now what do I do? We just want the curvature radius. Fine. So basically just want the acceleration at any given moment. That is complicated. I mean normal acceleration as well. So that's even more complicated. Just if there was some other way to figure out what the radius of curvature should be, wouldn't that be awesome? Right? That would be just really awesome. Okay, so the radius of curvature, it would be of that circle which fits the curve most neatly at that point, right? and it's only dependent on the geometry. It's not actually dependent on the motion, in fact. Exactly. So what if instead of having v over here, we had something else, right? Yeah. So for example, what if your equation was, let's say, uh, let's just say y is equal to a cube times t square and x is equal to 80. If this was, for example, your equation, then what would happen, right? So if this is how it was moving, then we could just find out what the normal acceleration should be at any point, right? Yeah, of course. This is also, but seriously, without doing anything like this, yeah, without parameterizing, how would we do it? Huh. Now that's more of maths questions, not physics questions. Radius of curvature at any. So what circle will touch it? I mean, there will be multiple circles that touch it, but the one that hugs it most. So second derivative of the circle at that point, right? I mean, basically d squared y upon d squared should match with the second derivative of that, right? That's how it should be. So you can say, all right, and this goes both way because x and y, they are kind of symmetric. So you can say d squared y upon dx squared is 0, and at the same time dx squared upon dy squared should be equal to 0. Awesome. And now how do we use this? No, it's not supposed to be 0. These quantities, these must be the same basically. Yeah, for this curve as well as for that curve, right? So the curve that I'm talking about is a circle. Ah, damn it. How am I supposed to solve this? Curvature at that point. Think about it. If something is on a circle, we do talk about how fast its tangential velocity vector changes, right? That curve is what we refer to as a second derivative. Now, if there was some other way to just not think about it in terms of second derivatives or something else, maybe, if you could think about something else, it would be just so easy to solve this, right? Yeah. I mean, okay, we can definitely create a family of circle which share the same tangent with this at a particular point. So let's do it, right? Let's do it. And wait, you only want at x equal to 0. This is actually even nicer because y equal to ax square like this, right? At x equal to 0, you know the circle is going to be like this. Oh, this is awesome. Fine, so that's nice. So just have x squared plus y minus whatever this radius is, r squared is equal to r squared, something like that. Okay, basically x squared plus y squared minus, let's not do that. And then what can we do? We can differentiate with respect to x and with respect to y. What if we use some other variable and wait a second, some other variable? Why not go for polar coordinates, right? So shift everything according to this thing, right? So once you got this point, which is 0 comma r in this case, it is actually much easier to figure out what this is. Yeah, and now I'll just shift everything for this point. So now this parabola, it will just become, so instead of x y, you have y. So with respect to this, your y coordinate, right? That the y that you're actually putting in this thing, that is in fact bigger than the y coordinate as measured from 0 comma r, right? So it should be y plus r. That thing is equal to a times x squared is still the same because no shift in x. So notice what happens. All the values uh, are basically, so all the y values, they are shifted down by r, right? Because then when you add r to now those values, it will shift them back. Isn't that right? That's why we are doing this. Awesome. So this would be the parabola as viewed from this point. So if I want to write it like this, will be the parabola. Okay, cool. And after this, what we want is to write everything in polar coordinates. This is going to be awesome. Of course, this will be awesome. Yeah, right. So in polar coordinates, you can just write x and y as, so let's call this in capital R. So this thing is going to be capital R, and this is the general radius small r. So you will have r sine theta, where theta is of course this angle, and that plus capital R is equal to a r squared cosine squared theta, right? That's what this parabola is like. And yeah, once that's done, we need to figure out what the curvature over here is, and then how do we figure that out. Think. Second derivative, right, should be same, but now it's not in dy upon dx anymore. Right, so right, your whole r theta relations should basically turn out to be this circle as we get close to this point, right? So this circle has the relation r is constant, so r is equal to capital R, right? So for anything that is in close proximity to this point, so this point is just in polar coordinates is r comma negative pi upon 2. So when it's in proximity to this, so we'll say theta is equal to minus pi upon 2 plus alpha. When you put that in here, you will just have r, right? So basically it should, and it's as alpha approaches 0, right? At that particular moment, your curve should just become small r is equal to capital R. Exactly. Yeah. Or you can think, okay, that happens, sure, your derivative of r with respect to theta is 0. That might be also one way of seeing it, because over here, as you can see, as theta changes, your r changes, and it keeps on going. But whenever it hugs it the most closely, what's happening is that the derivative, yeah, it's 0, because right now your r is decreasing and decreasing, and then it just touches, and then it starts increasing once again. So what's happening is that r gets to a minimum or maximum value, but I think minimum value. That's one thing that happens, right? But then you might say, okay, this also happens for this. So now what do I do with it? The rate of change of the derivative, that should also be, sorry, the rate of change of the rate of change of the radius r, like that thing should also be 0, I think. Now why would that be? That's still the big question. Why would that be? What does dr upon d theta actually represent? Well, it represents, okay, at this, yeah, so just think about it. It's a big circle. You have some curve like this, right, over here. If you zoom in, then this thing is dr, this thing is d theta, right? So your dr is increasing as you increase d theta, but then for this thing it's 0. Okay, that's awesome. Wait a second. Yeah, like at that particular point it's 0 anyway for both of these. Exactly. But then if it okay, I really want to just equate t square r upon d theta square is equal to 0. I just want to do that, but I can't explain why I want to do that. It's like if you keep on increasing, at some point it's going to become something like a circle. So it's just another layer of accuracy to it, right? So your d r upon d theta, maybe that corresponds to a first degree approximation, and then maybe third second derivative I mean it goes to the second degree approximation, something like that. It could be, right? Okay, let's think about dr upon dt right now over here. Okay, it doesn't have a geometric meaning right now. That's the whole problem. If it did have a geometric meaning, it would be so much better. Okay. So what would happen if your dr upon dt was 0 and d square r upon dt square was 0 as well? Well, then it would just become a circle. And that's why it is the closest approximation, right? You could think of it like that. So this circle would be the closest approximation to that if this happens. Seems legit? I think so. So should we just go with it? I think. Yeah, I'll just go with it. Or you could just use this thing. We'll try doing it both ways to see what we get. So first of all, we'll just put theta is equal to negative pi upon 2 plus alpha in this thing. Sine of negative pi by 2 plus at some angle, that's just negative sine of pi by 2 minus an angle, so negative cosine. So it's going to be negative r cosine theta plus r is equal to ar squared. So what's this thing? Cosine squared theta, and it's changing, so it's like sine squared theta. Ooh. Nice. Oh, sorry, it should be alpha. Right. So this is the curve at that point. So let's go for the Taylor series approximation for sine alpha and cosine alpha. Maybe that will give us insight into what is happening. So you see, for small r is equal to capital R, there's no theta dependence at all. So what if I said that small r is equal to capital R plus 0 times theta? That is, I am thinking of small r as a polynomial function of capital R. That would make sense, right? So maybe we can do the same kind of thing over here. Not exactly as polynomial function, but you get the idea that it's involving polynomial functions or rational functions or something like that. So then we can write cosine as 1 minus of theta squared upon 2 maybe plus r. So this will be till a second degree term. That's really nice, right? That's what I'm thinking of. It will give us two equations if we go till second degree terms, so that there will be no dependence on the linear term and the quadratic term. Those coefficients must be 0, probably. That's how we do it. I'm gonna read how to do it after I'm done with this question. So sine squared of alpha, it should be theta. Sorry, it should be alpha over there. Fine. Sine squared alpha is already, it's just alpha squared. Nice. So now what must happen is, so let's just do it. Negative r plus r alpha squared upon 2 plus r is equal to ar squared alpha squared. So for there to be no dependence on alpha, these two things must be the same. That is, yeah, this looks perfect. All right. So it's kind of complicated actually. Fine. So maybe like that. Right. What should happen is that ar squared will be equal to r upon 2. That should happen. What was a once again? Oh yeah, a is just this thing. But it doesn't involve, why is there this capital R over here? This should be gone. It should be gone. It's not supposed to be here. So for this to happen, your small r value, in fact, we got what it should be. Yeah, but that's not actually nice. It just tells us what, hey, wait a second. You know what the small r value should be? And once you know that, you can just equate this to capital R and you are done. Oh, yeah. So you can say, okay, R is equal to A upon, sorry, 1 upon 2A. That's what we got. I'm skeptical of this thing. So you're saying this thing is 1 upon 2, but it could be anything. It could be anything, but we got 1 upon 2A. That probably means it is the radius. And this R is also equal to capital R. That's the main thing. Capital R is equal to 1 upon 2A. That means the radius of curvature is 1 upon 2A. Now, this is a nice method. Let's see if what I thought is correct or not. That the second derivative being equal to 0 with respect to theta, of course. That would also mean the same thing. Maybe. So we'll take a derivative of this thing, which is theta. So then that will be r cosine theta. Okay, that's gone. Is equal to yeah, and we just want dr upon, oh, so r also changes, right? You should also account for that. Then it's going to be dr upon dt. Okay, so dr upon theta is 0, dθ is 0 anyway. So you can just directly write this as r cosine theta is equal to ar squared. So 2, then it's supposed to be negative 2ar squared cosine theta sine theta. This should happen, and at the same time, what should happen is that, and this is supposed to happen at alpha. Sorry, at theta is equal to negative pi upon 2. Sorry, that would make more sense. So at negative pi upon 2, well, this is gone. This thing is gone as well. So it happens by itself because we set it like this, right? So it's supposed to happen like that. Now, what else can we do? Just take the second derivative. So this should happen. Now, going for the second derivative, it will be negative r sine theta is equal to, so this is like negative ar squared sine 2 theta, taking the derivative of that thing. That will be negative 2ar squared cosine 2 theta. This should happen. Exactly. And that is, of course, at theta equal to negative pi upon 2. So this will be negative pi right there. That means it will be negative 1. So 2ar squared, and at negative pi upon 2 is also negative 1. So r. And there we go. We also got r is equal to 1 upon 2a from here. That means both of my methods are going for the correct thing. That we are approximating it as a circle at that particular point. So this is a nice way to do it, I guess. And then of course there's that way you can just have dy upon dx equal to 0 and d squared y upon dx equal to. But for that you need to build up the circle in x squared and y squared, which is seriously it's not nice. Don't do it. But hey, we got it, huh? We got what this should be. Perfect. So you got, so we can definitely find the curvature radius, right? So for a, you will just have the curvature radius is 1 upon 2a, and from that you can easily figure out what the acceleration should be. It will be a piece of cake now. So your acceleration will be w, right? That will be v squared upon r, which is 2av squared. Perfect. Now let's go to b. This is an ellipse. So x squared upon a squared, all that stuff, right? So it's something like that. Now at x equal to 0, right? Oh, so this. Hey, I remember I actually did derive something for this, but now I don't have it in my mind anymore. So yeah, I mean, you have 2 points, so just go with the upper part because it's symmetric anyway. So we'll say this is radius r, well, this completing is just b. So then this is b minus r. So our point is 0 comma b minus r, and the other point that, okay, this passes through, that will be 0 comma b. So we can figure out what the circle should be. So it's just going to be x squared. Oh yeah, so in fact don't even figure out what the circle should be. Once you got what the circle's center is, just shift everything to that. So the way to do it is y plus the y coordinate of this circle. That's now I know it because we did it in the previous case. So it's going to be plus b minus r. Now this is the kind of question I wanted to have that would give me some insight into something that is not the routine thing, right? So plus b minus r. that thing squared. So that upon b actually squared plus x squared upon a squared, right? Because no shift in x, that's equal to 1. That's our thing. Now, yeah, we can write y as r sine theta and all that stuff. Cool. Let's try to do it. So it'll be r into 1 minus sine theta that upon b plus 1 squared plus now it's going to be r squared cosine squared. Yeah. So upon a squared cosine squared theta is equal to 1. Perfect. And now what? Take the derivative of this thing with respect to theta. Equate that to 0. Well, that's going to be obviously happening. You can take the second derivative and equate to 0. That would be the less obvious thing. But first, we've got to expand this actually. 1 plus, or we could just go for the approximation that we did the last time, because that in fact was much more cleaner, right? Don't you agree? So for this case, it's touching at, I mean, when it won't work, it won't work. But right now it is working, so we'll just go with it. Perfect, right? Yeah. And speaking of ellipses, I mean, you know, you have elliptical orbits. So from that as well, I guess we can figure out the radius of curvature. So as a general function of the eccentric angle. That would be super cool to do. Anyway, for this particular case, you just have theta is equal to pi upon 2, right? So we will say theta is equal to pi upon 2 plus alpha, because I want it like that. So then this will just become y, what? Okay. So then it will just become r into, so 1 minus sine of this kind of thing. That's just 1 minus cosine alpha upon b plus 1 squared. R squared upon a squared, and then cosine squared alpha will get, we can write that as sine squared of, yeah, squared, right? So the negative sign goes away, and then square this. Oh, it's gonna be not nice. Okay, but we have to do it anyway. What if I write it as r upon b plus 1 minus r cosine? Okay, that's just too much. So 1 plus 2 r upon b into 1 minus cosine alpha plus this thing squared. Or we could just directly go for the second degree approximation and say, okay, this thing is just alpha squared upon 2. That would clear up a lot of things for us. So then it's just going to be 1 plus r alpha squared upon 2b squared plus, right? And all the alpha squared terms, those must be cancelled out exactly as we did previously. Nice. Now to the r squared alpha squared upon a squared. I don't want to confuse alpha with a, but I have high probability of doing that right now. So this is going to be 1 plus 2r alpha squared upon 2b plus, now this is weird, it's got alpha power 4 over here, huh? But you know what, we'll ignore that. Exactly, we'll ignore that. This makes it so much easier to work with. Yeah, much better than doing derivatives and whatnot. At least for this case. Who knows what will happen at some other case. R squared a squared upon, sorry, alpha squared upon a squared is equal to right, this one cancels, and wait a second, is this supposed to happen? It's 1 minus cosine, and that's supposed to be 1 minus of alpha squared upon 2. Yes, something's not right about this. It's supposed to be cosine. Yeah, sure, it would be definitely, it would just be alpha squared upon 2. Oh, no, it's correct. Okay, no problem with that. It is correct. Then where did I go wrong? Here's where I went wrong. R sine theta, so then it should be negative right there. So then it will be negative over here, and then it will make sense. Okay, cool. So time to cancel some stuff out. Okay, why is this 2? Oh, nice, cancels out. Alpha square cancels out. right? Then you just have r upon b is r squared upon a squared is equal to 1, right? R will cancel out, so just, sorry, equal to 0. What am I doing? Negative over there as well. So r upon a squared is equal to 1 upon b. There we go. R is equal to a squared upon b. That should be doing it. And I think by symmetry, it would be okay to assume that over here, radius of curvature would be, I don't know, b squared upon a. To me, it looks like that would work. So we got it. The radius of curvature is just a squared upon b. And the acceleration, so the centripetal acceleration, that is. Wait, what do you want? You want the acceleration, not the centripetal acceleration, the total acceleration, you say. But the v doesn't change, right? So tangential acceleration is 0 anyway. Nice. So then it's just w is equal to the v squared thing upon this radius. So b v squared upon a squared. This was awesome, right? Learned something new today. 43. So I'll try to see if there's a better way to doing it. You know, because I wanted to do at any single point, and I don't want to form the whole circles equation, and yeah, no, I don't want to do that, right? Of course. Yeah, next. Okay, 43rd, a particle A moves along a circle of radius capital R is equal to 50 centimeters, so that its radius vector relative to the point O, 1.5, this thing. Oh, so O is somewhere over here, that's awkward. Rotates with constant angular velocity, omega is equal to 0.4. Fine. Rotates. Wait, what? Oh, circle of radius R is equal to, so that's radius vector R related to the point O rotates with. Oh, this is very nice, huh? Find the modulus of the velocity of particle and the modulus of the direction of its acceleration, I guess, as functions of the angle and everything. Okay, it rotates with a constant angular velocity, you are saying. Huh. This is weird. And the modulus of the direction of its total acceleration. So they didn't give us at what point we want to do this, or any angles or anything. They didn't give us anything, right? But they did give us what r vector is. So maybe with r vector we can figure out what this should be. Right, so we'll have to do everything using r vector itself. I think so, that's the only way. Okay, so let's try to do it. We'll just take this center to be our origin, then this thing, this point is just, it's crazy, right, to see O as not being used as the origin, but that's how it is. So it will be negative capital R comma 0, and this point is, so our point A, that's just r cosine theta upon, and then comma r sine theta, and yeah, so your r vector, that will just be equal to this as that, which is r cosine theta plus capital R and then r sine theta. And so now what's the angle that this makes with the x-axis? That would be tan inverse of y coordinates, r sine theta upon r cosine theta. So hey, why is this? It's supposed to be capital R, sorry, plus r, which is basically just tan inverse of sine theta upon cosine theta plus r. That's, let's say it's alpha. So our d alpha upon dt is a constant. It's omega, right? So omega is the derivative, time derivative of this thing. So that will be, let's just call this thing omega alpha, whatever. Okay, maybe we should have not used alpha. Let's use something else. Call this thing, I don't know, phi. So d5 upon dt is omega, and let's say that d theta upon dt is oh no, d theta upon dt should also be omega. It's not use omega for this, but they used omega, right? Yeah, they used omega, so we have to stick with that. This is such a problematic thing. Theta upon dt, what will we call it? Just call this thing. Just call this thing d theta upon dt. Yes, don't name it anything. Fine, and then the derivative of this thing with respect to theta. So, oh god, this is so weird. Oh, it's supposed to be 1, sorry. Hey, you know what? Write it in a different format. So 2 sine of theta upon 2 cosine theta upon 2 cosine square of theta upon 2. That looks nice. And this will just be tan of theta upon 2. So tan inverse of that thing, it's the same thing as theta upon 2, right? And that at least for this range, sorry, this range where theta is in the first quadrant, then it will work perfectly. So you can see, I mean, okay, it's kind of obvious that this angle has to be theta upon 2, because if this angle is being theta, right, so by the angle subtended theorem for circles, you can see this is only theta upon 2. Obvious. Fine, and that means, okay, oh come on, this was so easy. The angular velocity of this guy, I mean with this guy, or in fact any point on this circumference, is just half of the angular velocity. I mean the actual angular velocity, which is, let me, come on, d theta upon dt is just 2 omega. That's all you wanted to say, huh? Fine. Now, what do we want with it? Find the modulus of the velocity of the particle and the modulus and direction of its total acceleration. So this is going to be 2 omega times the radius of capital R. That thing is the tangential velocity. And there's only tangential velocity. There's no radial velocity over here. So yeah, V is equal to this. Obviously 2 WR. 2 omega is better. Okay, and find the modulus of velocity and the direction of its total acceleration. Oh, so it's v squared upon r in that direction, and there's tangential acceleration. No, there's no tangential acceleration, just moving at a constant. So yeah, so acceleration is radial. They just want a direction, they don't want the magnitude. Cool. Oh, okay, they also want to make it, and the modulus and the direction. Fine. So we'll just say a vector is equal to v squared upon r, which will be this thing squares, like 4 omega squared r squared, and that upon r. So 4 omega squared r, but in negative theta hat. Sorry, negative r hat. That makes sense. Okay. Let's go to 44. A wheel rotates about a stationary axis so that the rotation angle phi varies with time as phi is equal to 80 squared. Stationary axis. What? Oh, okay, fine. So the wheel is something like that. It's just stationary axis, rotates about this, right? So that the rotation angle phi. So maybe like this is the angle that's making phi. Varies with time as phi is equal to 80 square, where, okay, whatever, we don't care what a is. Find the total acceleration, w of the point a at the rim of, at the moment t is equal to 2.5. If the linear velocity of the point a, wait, what? Oh, so it's angle varies like this. Of course, it's at constant angular acceleration. So why even? Okay. So does that t equal to 2.5 really make any difference? Linear velocity is v equal to 0.6. Man, you gave us everything now. Seriously. Oh, so okay, now I get it. Yeah, it's like the centripetal acceleration, that actually is time dependent. But they gave us the linear velocity at that moment. Man, how can one be? Oh, wait, no. Okay, you don't know the radius. That's the thing that it didn't give us, right? Exactly, they didn't give us the radius. That makes sense. So you can figure out what the angular velocity should be at that particular point, right? And then you will just have to use omega squared r. There's no other way. Yeah. So you gave us the velocity, it's of no consequence. Still, think about it. If you want to eliminate radius, how would you do that? So you're like v is equal to omega r. What we actually are looking for is half, sorry, no, not half. What was I doing? We are looking for omega squared r. That's the centripetal acceleration. So that is just omega times omega r. It's like omega times v. That's kind of nice to think about it. Yeah, awesome. So we just need omega, which can figure out easily, and time. So what's omega? Omega is just d5 upon dt, which is 2at. So at t is equal to 2.5, you can figure that out, all that stuff. Yeah, and then the v that they gave us. Cool. Once you got that, you will have the centripetal acceleration figured out, and the tangential acceleration is kind of constant. Perfect. So let's do it. The tangential acceleration is so the second derivative of this thing, right? So d squared 5 upon dt squared. Oh, that would be the angular acceleration. Sorry. Angular acceleration. So, you need r once again. Why? Once is not enough. So you need to figure out what r is. Otherwise, it's just not doable, huh? Fine. So, omega, that is 2at. They also gave us all the values and all that stuff. Fine. And that's equal to v. So you can say, it's only v upon r. So you will have r is equal to v upon 2at. That's our first thing. Now our tangential acceleration, the angular acceleration, that thing is just 2a. So you can say tangential acceleration is just this times the radius. So that will be 2a times v upon 2at. So it's going to be v upon t. Nice. Which makes sense, of course. Right? So if this is at constant angular acceleration, this goes from this to that. Yeah, whatever. And the centripetal acceleration is just v squared upon r, which will be, so v is gone. I mean, v is given upon r. R is just this thing, so v, and then got 2at like that. So it's gonna be 2avt. Make sense? Cool. So, and what do we want? What do we want? Total acceleration. So, I mean, as a vector, I think so. Fine, I'll do it as a vector. So, acceleration is, oh, they already used a everywhere. So instead, we'll just have to use w. So this will be this v upon t, right? So v upon t times theta hat, and then minus 2avt times r hat. There we go. Now time to figure out what this actually is. So what's v upon t? It's 320. Wait, no, that's not 45. One here v is 0.65, and that upon t is 2.5. So 0.65 upon v upon t. 0.65 upon 2.5, which is basically like 65 upon 250. Should make sense. And divide by 5. So it's gonna be 13 upon 50. Multiply by 2, so 26, 0.26. So that's supposed to be 0.26. V upon t is 0.26. And what is this thing? It's just 2avt. What's v times t? Come on. Are you serious? Just do it the normal way. So 2 into a is 0.2 into v, which is 0.65, into t, which is 2.5. That should be it. So 0.2 is 1 upon 5. So you can say this times that, it just gives us 0.5. And then this and that is 1. So it's just 0.65. So this is just negative 0.65 r hat, and This thing is just, I hope this is actually correct. What's the units? A was in radian per second square, then V was in meter per second, so it's gonna be radian meter per second cube. But then radian meter is just it's just meter itself, so it's meter per second cube, and then that times T, so it's gonna be meter per second square. Nice. And V upon T is obviously acceleration. That was just 0.26. That's it. That's our acceleration. There we go. Should I give the magnitude of this thing? I don't think so. Okay, let's go to 45th. Okay, acquires velocity 320 having made n equal to 2 turns inside the barrel whose length is equal to 2 meter. Wait, what? Barrel? Turns inside a barrel. What shell? What are you talking about? What barrel? Length of the... I am not understanding. Can you draw a figure for this? This makes no sense. We're talking about a shell inside a barrel. What does that actually mean? Turns. And shell of what exactly? Huh? Length is given. Okay, maybe like this. This is this thing. So it's a long barrel, and then maybe shell is some kind of ball, or I don't know. And then it's a ball, and it's rolling, something like that. Do you mean like that? Inside a barrel's uniform acceleration. All right. Find the angular velocity of its axial rotation at the moment when the shell escapes the barrel. Of its axial rotation, right? So along this axis that's going out, of course. It's doable, I think. So if it's pure rolling, is it just rolling? Do we have to assume it's pure rolling or not? What if it's just metals and it's like very smooth metals? That would mean this is just sliding and rotating, and rotation is not actually doing anything. Find the angular velocity of its axial. Okay, this is weird. I'm just leaving it because I don't understand what they are trying to do. What kind of... They didn't even give us a picture. What am I supposed to do with it? Okay, 46th. First of all, they didn't tell us if it's pure rolling or not. They didn't describe the situation actually. They didn't tell us if it's moving rectilinearly or not. They told us nothing. They just told us there's a shell inside the barrel and it's making turns. What does turn mean? Turning about what? What axis? Is it moving linearly? Is it pure rolling? Give us something. Okay. Next. A solid body rotates about a stationary axis according to the law phi is equal to 80 minus pt cube. Oh, look, this kind of question, it's descriptive, it's giving us everything. Nice, right? The stationary axis, okay. Yeah, and we are given. Find the mean values of the angular velocity and the angular acceleration averaged over time interval between t is equal to 0 and complete stop. Angular velocity and angular acceleration. Oh, okay, got it. So its angular changes from something to something, that upon time. And complete stop. What do you mean complete stop? Will this actually completely stop ever? I don't think so. I mean, its angle is changing like this. So Yeah, I don't think it will completely stop. What does the complete stop mean? I'm going to assume they mean the first time it stops after t equal to 0. That would be when you have t squared is equal to, sorry, it stops. That would mean your your omega is 0, not that. Fine. So your omega is just a minus bt. So yeah, so at t equal to 0 it's not stopping. So when they say complete stop, they do mean omega is 0. Just that. So just two t values. One is negative, which makes no sense, and one is positive. Just have t is equal to square root of a upon b. That's when this will stop, right? And we want the, so first of all, what's the mean angular velocity? So omega average, that will be, so the phi in that in that time, right? Which is just at minus bt cubed really, and that upon the time, so just a minus bt squared. Oh wait, it's not supposed to be like this. It's supposed to be a little bit of mistake, sorry. It's supposed to be a minus of 3bt squared. So t would be square root of a upon 3b. Fine, and this thing is going to be a minus bt squared, exactly. And then just put that t in there. So t squared is equal to a upon 3b. Going to put that in there. A minus, so b into a upon 3b. So just a minus a, like 2/3 a. There we go. We got the first quantity, 2/3 a. Let's go for the average angular acceleration. So initially at t equal to 0, omega is a, and t equal to this thing, square root of a upon 3b, your omega is 0, right? Because it a complete stop. Yes, so your average acceleration, sorry, angular acceleration is just, so it went from a to 0, so it's negative a upon the time required, which is just this thing, so square root of a upon 3b for the complete stop. So it's only negative square root of 3b upon a. That should work. I hope so. Square root of 3b upon a. Oof, this is wrong. Now it's done. Okay. 47th. 47th is a solid body starts. Oh, sorry. There's also the part B over here. Oh, okay. This is part A. Let's go to part B now. Let's go to B. Yeah. Oh, and just by the way, the dimensional analysis is thing. So A is having units per second, and this is also per second. So this makes sense. And then what about this guy? So it's square root of 3b upon a. Well, B has so time power -3, and that upon a is going to be time power -2. Square root of that is time power -1. Wait, what? No. It's time power -3, and that upon time power. Uh-oh. I messed up somewhere, didn't I? Yeah. What it's supposed to be negative a upon square root of a upon 3b. Oh, so it's supposed to be square root of 3b times a. I knew I would mess up sometime soon. Yeah, it's like 3ab. Sorry, now it's correct. Yeah, it really is a good hint that this book gave me. That just derive everything general form and then do dimensional analysis. It really saves us sometimes. Okay, B. The angular acceleration at the moment when the body stops. When the body, okay, so at that point, what is alpha? Why did I erase all this? Okay, so omega was a minus 3b t squared, so alpha, which is equal to -6p times time. Now, we know what time is, so -6p square root of a upon 3b, I guess. Looks nice. So this will be negative 2 square root of 3ab. Nice, isn't that? So yes, your angular acceleration, that was just negative 2 square root of 3ab. Okay, cool. Now let's go to 47. Solid body starts rotating about a stationary axis with an angular acceleration. This thing is okay, whatever. Stationary axis, angular acceleration is given. How soon after the beginning of rotation total acceleration vector of an arbitrary point on the body form an angle alpha is equal to 60 degree with the velocity vector. Oh, right. So yeah, it's just some kind of rigid body. So for some point its radius r. This thing is the tangential acceleration for that particular point, right? And this is the centripetal acceleration. So what you want is that this angle with the velocity is also in this direction, of course. That would be 60. Now the good thing is that this is just r alpha, and centripetal acceleration is just omega squared r. So when you divide this, right, and you have to divide it, we are dealing with AC upon AT, I guess, right? Yes, so tan alpha is equal to, I mean, I don't like this alpha over here. So I will have to use beta, but seriously, why? Okay, that is just AC upon AT, which is omega squared upon beta. There we go. That's what we need to find out. And now omega squared is the main thing. Beta is already given to us. This will be the thing. So tan alpha is equal to omega squared upon beta. And you have angular acceleration given. What is omega squared going to be? Initially what? So it says it starts rotating. So I'm going to assume that initially your omega was 0. So that would really mean that you can just integrate it. What am I doing? So this is d omega upon dt. So we just have omega is equal to half of a t squared. That's weird. It's very weird. That's how it is. Fine, in the square of that. So this thing will just be, for this thing squared. Man, angular acceleration, this is non-uniform. Wow. That's new. Radial acceleration is 0 anyway, right? Sorry, no. What am I doing? The centripetal acceleration is omega squared r, right? Why am I doing this? We already did this derivation already. So now it's just omega squared upon beta, without doubt. So half a squared squared is going to be 1/4 of a squared to power 4, and that upon this thing. So a times t. Cool. That should just be equal to 1/4 of AT cube. I hope this is correct. It was supposed to be a square t power 4 upon this, right? What else? So that is, I mean, it's just an angle, of course. So look, this has per second square over there. This is in seconds, so per second cube would be what a is. So this will be pure number. Makes perfect sense. Okay, so that's it. We have it right there. And now just put in these values. So you have yeah, how soon after the beginning, right? Cool. You just need a for this and alpha for this. So tan alpha in this case is square root 3. Square root 3 is equal to 1/4. So like 4 square root 3 is equal to a, which is 2 into 10 power negative 2, and that times t squared. Wait, what? Sorry, t cubed. But still, it's radical of radical. This is just okay. So 200 square root 3. What is this? Cube root of that thing. Are you serious? Fine. It's gonna put in there. The time required is the cube root of 200 square root 3. Whatever that is. This is weird. Okay. So let's go to 48. Maybe I should stop now. I don't know. How much is remaining? So till 58. Right. It's about 10 more questions. So I think we should stop and I'll do the last 10 questions in another video. So we did till 47. It's good enough. Where it go? Okay, so we will stop here. I'll see you guys in the next video.